Alright, you guys, so we are continuing to solve triangles. In section 4.4 and 4.5, we are going to be solving oblique triangles, so non-right triangles. And in section 4.4, we are using the law of sines to solve certain oblique triangles based on the information that we are given about the triangle. So remember, there are oblique triangles and there's right triangles, and then of oblique triangles, we have acute triangles and obtuse triangles. So that's what we're going to be solving for. Here's our labeling for the triangle. So we're using the capital Greek letters alpha, beta, and gamma to label the angles, and lowercase a, b, and c to label the sides. Okay, so we're going to be solving oblique triangles when we know one of the sides and then either two angles of the triangle, one angle on another side, or the other two sides. So here are the first two cases, which these are the two cases that we're going to be solving using law of sines. And case one is angle, angle, side. So if you're given an angle, another angle, and a side, angle, side, angle. And then case two is what we refer to as the ambiguous case. And it's when you're given a side, and an angle. Or the way to remember that's kind of a special case is in the reverse. So ASS, angle, side, side. So again, we're using law of sines to help us solve these two cases. In the remaining two cases, case 3 and case 4, so if we're given a side, angle, side, or all three sides, we're going to be looking at in section 4.5 and using law of cosines to solve those triangles. And remember, there's no, you can't solve a triangle when you're given all three angles and none of the sides, because remember the definition of similar triangles. Basically, if we're given three angles, there's infinitely many triangles that we could construct or find the sides for. So here is law of sines, and law of sines can also be flipped. So it can be written as A over sine of alpha equals to B over sine of beta equals to C over sine of gamma. So for example, if you're solving for an angle, alpha, beta, or gamma, it's usually helpful to write with the sine of alpha or the sine of beta in the numerator, versus if you're solving for a side, it's going to be less steps if you have A, B, or C in the numerator. But if you just want to stay consistent and use sine of alpha over A, sine of beta equals sine of beta over B equals sine of gamma over C, that's totally fine. In our textbook, that's how she does it. And then just a side note that remember that the longest side of a triangle will be opposite its largest angle, and the shortest side of a triangle will be opposite its smallest angle. Okay, so here is case 1. So we need to solve this triangle. So the first thing that sticks out to me is we're given two angles, so we can solve for that remaining angle, gamma. Let's use a different color. Because we know that the angles must sum to 180 degrees. So gamma will be equal to 180 degrees minus the sum of those two angles. So gamma will end up being equal to 32 degrees. Okay, so now we have all three angles, and we can solve for the missing sides, so side A and side C. We want to use the given information as much as possible when calculating or doing those calculations, finding those sides. But in this case, it doesn't really matter. We have the exact angles. So why don't we just go in alphabetical order? So we can use sine, or since we're solving for a side A, Why don't we put the sides in the numerator? So we'll do 30 over sine of 43 degrees equals to A over sine of 105 degrees. So now to finish solving for A, we can multiply by sine of 105 degrees on each side. Okay, then we can pop into our calculator to get our approximation. Remember, we're rounding to 4 decimal places. Make sure that your calculator is in degrees. Usually when we're solving triangles, we're going to want our calculator in degrees. So we get 42.4895 degrees. Oh, it's not degrees, it's side length. So we get 42.4895 for side A. So now we're just missing side C. So again, we can use 30 over sine of 43 degrees equals 2C over sine of 32 degrees. Multiplying by sine of 32 degrees on each side, we'll have 30 times sine 32 degrees over sine of 43 degrees. So side C will be approximately 23.3103. Double check I typed that in there correctly. Yes. Okay. And then remember, I would like, well, I guess if you weren't in class today, you wouldn't remember, but I would like you guys to summarize your solutions by listing all of the angles and sides. Oh, and the sides are in feet. Okay, so you can summarize like that. That'll just make it a little bit easier for me to follow your work. Okay, this is also, this is still case 1, just another example where we're given angle, side angle. So you can find alpha first and then go ahead and use law of sines to find side C and side B. But let's look at case 2, the ambiguous case. And it's called the ambiguous case because there can be, with the given sides and angle, that information can represent 1, 2, or no triangles. I told the class today that I will not ever give you guys on an assessment information that results in 0 triangles. So if you end up with the ASS case, the SSA case, then there's either going to be 1 or 2 triangles. And the method that I'm going to have you use, I did explain in class today how you could end up with 2 triangles. Because I don't want this video to be incredibly long, I'm just going to show you guys the method that you can use when you run into this case. And it's in your textbook, or I have notes if you're curious about how to analyze the given information to determine whether there's 1 or 2 triangles or no triangles. Okay, so here If you weren't sure, you could always draw a picture of a triangle, labeling the angles and the sides, and fill in which information you are given to see that you have the SSA case. So the only thing that I can do right now, the next thing I have to solve for is going to be angle gamma. So I can use law of sines, and I'm going to do sine of 133 degrees in the numerator, since we're solving for an angle right now. Okay, so then if we multiply by 17 on each side of the equation, okay, so this is going to be a positive ratio. So if we think about what angle, we're solving for gamma, and gamma would end up, whatever that angle gamma is, would make this a true statement. The thing is, thinking back to like our unit circle, we know that there's actually going to be an angle from quadrant 1 that would make this a true statement, and an angle from quadrant 2 that would make this a true statement. So if you think about the unit circle, right, and if this is 30 degrees, we know this point is root 3 over 2, comma 1/2. Then this side, or this point, which is symmetric about the x-axis, would be negative root 3 over 2, comma 1/2. And this angle would be 150 degrees. Well, notice that sine is equivalent, for sine of 30 degrees is equal to sine of 150 degrees. They're not coterminal angles, but those angles are supplementary to each other, right? 150 degrees plus 30 degrees, they give us 180 degrees. So there's always going to be an angle from quadrant 1 when sine is evaluated for an angle in quadrant 1. Will give us a positive ratio, and an angle from quadrant 2. Now when we use inverse sine here, inverse sine is going to give us an angle from quadrant, will give us an angle from quadrant 1. And when we study the inverse trig functions, we'll go into more depth of why that is, but for now I'm just going to tell you because it's a function, and functions have exactly one output for every input. So if we find what gamma is by typing this into our calculator, I get gamma is approximately 15.01120. Okay, so notice that that is an angle from quadrant 1. So if we were to substitute 15.0120 degrees in for gamma, that would make this a true statement. Now, we need to test to see, because triangles can have obtuse angles. Now in this case, notice that the angle that's given is obtuse. So this is actually an indicator that there is only one triangle, because a triangle can't have more than one obtuse angle. But if it did have an obtuse angle that we were solving for, we could test for a second triangle by finding the angle gamma. So this is attempting to find a second triangle. So finding gamma for triangle 2, that's supplementary to 15.0120 degrees. Okay, and the angle that we end up with would be 164.9880 degrees. Okay, remember the angles of a triangle must sum to 180 degrees. Well, this would mean that alpha plus gamma would be greater than 180 degrees. Therefore, there's only one triangle. So we can test every time we run into the SSA case. If you're not sure if there's a second triangle or not, you can go ahead and check it. Okay, so we can go back to just solving for our one triangle. We now have gamma and we can solve for beta by subtracting the sum of the two angles that we now know from 180 degrees. So that's an approximation. Okay, so you get 31.9880 for beta. And I usually label these, like if I'm testing for a second triangle, I label this as gamma sub 1 and this is gamma sub 2. But there is no second triangle, so we don't really need to in this case. Okay, so now we need to find side B. Side B is all that we're missing. So use the given information as much as possible. So 48 over sine of 133 degrees equals to B over sine of 31.9880 degrees. So B equals to sine of 31.9880 degrees times 48. Oops. Over sine of 133 degrees. So B is approximately 34.7679. I think this is in meters. Our sides are in meters. Okay, so we can summarize all of our information. Oh, we were given C, huh? Okay, so there's the summary for this triangle, all the angles and sides. So let's look at the next example. So it's another SSA case. So we need to solve for angle beta first. So sine of 72 degrees over 8.1 equals to sine of beta over 8.3. So to find beta, we're going to take, I'm going to flip this around. So we're going to take the inverse sine of 8.3 times sine of 72 degrees over 8.1. So we get beta is approximately 77.0432 degrees. Okay, so I'm going to call this beta sub 1, and I'm going to try and find a beta sub 2, so a beta for a second triangle. And that would be supplementary to beta sub 1, so 180 minus 77.0432 degrees. And we get 102.9568 degrees, which makes sense with 72 degrees. So gamma in the second triangle is going to be small, but it will exist. So gamma would be 180 degrees minus the sum of the angles that we know. This is gamma in our second triangle. So you get 5.0432 degrees, so small, but still there. So let's find gamma in our first triangle. Okay, so again, subtracting from 180 degrees, the sum of the angles that we do know for that first triangle. Okay, so now we need side C for each of these triangles. I'm going to add a page. Okay, so side C, oops. So using the given information as much as possible. Okay, so C, I'm going to flip this, will be 8.1 times sine of 30.9568 degrees over sine of 72 degrees. So C is approximately, or this is C sub 1, right? Sorry, I think I typed something in wrong. You get 4.3810. Didn't seem right. Okay, and then if we solve for side C over on this side, okay, so T sub 2 will be equal to 8.1 times sine of 5.0432 degrees over sine of 72 degrees. I feel like I did something wrong in that first triangle. That side doesn't seem right. You guys will have to let me know if you find an error. So 0.7487. Oh, and our sides are in meters. Okay, so we have two triangles to summarize now. Triangle 1, alpha 72 degrees, same with for triangle 2. Beta made it over here. Gamma and our sides. Okay, so there's a summary of our two triangles, the angles and sides for each triangle. And this last example is also the SSA case, but in looking at the given information, notice that we have angle alpha is 107 degrees. So it's an obtuse angle, meaning it's going to be the largest angle of the triangle. The side opposite to 170 degrees is 6. However, since 170 degrees is going to be the largest angle, that means that the side opposite that angle should also be the largest. But here we could see that B is actually larger than A. And you would end up with an error if you didn't notice this and you went to solve for beta. You would notice, you would get sine of 107 degrees over, when you set up sine of 107 degrees over 6 equals to sine of beta over 8, okay? When you're solving for beta, so you take the inverse sine of 8 times sine of 107 degrees over 6. When you try and put that into your calculator, you get a domain error. And that also indicates that there is no triangle. Remember, I told you guys I'm not going to actually give you this, but I wanted you to see what an example would look like. You never know if you come up with one on a standardized test or something. Okay, let me know if you have any questions. Send me an email, come to Math Lab, or we can set up a time to meet.